Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and this episode is about a technology that can make things cold using nothing more than the vibrations of air. Imagine a world where your fridge doesn't rely on chemical refrigerants, your AC hums quietly instead of rattling with compressors, and even insensitive scientific equipment can be cooled without the risk of leaks or environmental damage. At its core, the concept is surprisingly simple, yet elegantly strange. Sound, as we usually think of it, is just waves of pressure moving through a gas. Yet when these waves pass through air or another gas, they cause tiny parcels of the gas to compress and expand. And here's the key. When you compress a gas and it heats up, and you can expand it and cool it down. By carefully orchestrating this process inside a specially designed device, you can create steady movement of heat from one place to another, effectively producing cooling without moving parts or harmful chemicals. With the right arrangement of tubes, stacks, and sound waves, it's possible to build systems that can cool rooms, electronics, and even reach temperatures needed for advanced research applications. It's a perfect example of how the understanding of physics and waves and thermodynamics can lead to entirely new ways of solving everyday problems. The effect was first hinted at in observations from over a century ago, but only recently have engineers and scientists developed designs that make the process practical and efficient. It combines engineering with physics, gases, resonance, and heat transfer, transforming what might seem like a curiosity into a usable technology. And we have a name for this remarkable process. It's called thermoacoustic cooling. And over the course of this episode, we're going to explore exactly how it works, why it matters, and what engineers are doing today to bring it out of the lab and into the world. The story of thermoacoustic cooling begins over a century ago with some curious observations about sound and heat. In the late 1800s, a British physicist noticed something remarkable. When sound waves travel through a gas, they can actually cause heating and cooling in predictable ways. He wrote about it in his classic work called The Theory of Sound, noting that compressing air makes it warmer, while letting it expand makes it cooler. At the time, this was more of an academic curiosity than a practical tool, but it laid the foundation for everything that would come later. Through the early and mid-20th century, scientists experimented with these effects in various forms. They explored how standing waves in tubes could move heat back and forth, and tried different gases, resonators, and temperatures. Many of these experiments were small-scale and limited by the materials and instruments available, but they consistently showed the same principle. Sound can move heat. It wasn't until the later half of the 20th century that engineers began seriously considering practical applications. With advances in materials, electronics, and precision machining, it became possible to design devices where sound waves could reliably move heat, rather than just produce small, transient effects. Researchers built the first prototypes of thermoacoustic coolers and demonstrated cooling without conventional refrigerants. Even then, the technology faced challenges. Early devices were insufficient, bulky, and difficult to control. It took decades of refinement to develop systems that could achieve meaningful cooling in compact, usable forms. By the end of this journey, engineers and physicists had laid the groundwork for the modern thermoacoustic devices we explore today. Systems that harness the vibrations of sound to move temperature in ways that were once impossible. At first, the idea that sound can move heat might seem completely counterintuitive. After all, we usually think of sound and temperature as something completely independent. Sound is something you hear, not something that can make ice cream cold, or a lab instrument operate more efficiently. But when you understand what sound actually is, it starts to make more sense. Sound is nothing more than oscillating pressure traveling through a medium, usually air or another gas. Imagine a wave traveling through the air around us. Regions of high pressure, where the air molecules are tightly packed, alternate with regions of low pressure, where the molecules are spread farther apart. This compression happens with thousands of times per second in a typical thermoacoustic system. Now here's the crucial point. When a gas is compressed, its molecules are forced together, which increases their kinetic energy and therefore the temperature of the gas. Conversely, when a gas expands, the molecules spread out, slow down, and the gas cools. Thermoacoustic cooling is about harnessing this repeated compression and expansion in a controlled way to move heat from one location to another. The very start of this process is the driver, which is what creates the sound waves that make the cooling possible. In most thermoacoustic devices, the driver is like a loudspeaker that pushes the gas back and forth to very high speeds. You can think of it as the engine of the cooler. It puts the air into motion, generating the pressure oscillations that will eventually move temperature through the system. The heart of a thermoacoustic cooler is the resonator, which is basically a specially shaped tube that lets sound waves from the driver bounce back and forth. You can think of it like blowing across the top of the bottle. The sound you hear comes from the air vibrating inside the bottle in a specific way. Inside the resonator, the sound waves form patterns called standing waves. And these patterns, some points, called nodes, barely move at all, where other points, called antinodes, move a ton. By choosing the right tube length, gas, and sound frequency, engineers can control exactly where these moving and still points happen, which is essential for making the cooling process work. Inside the resonator sits a stack, which is a material made of thin plates or parallel channels. This is where the magic happens. The stack is placed strategically at a location along the wave where the gas is oscillating in just the right way, just the right amount. Tiny parcels of the gas move back and forth through the stack as the wave passes. When the gas is pushed toward a hot surface in the stack, it absorbs heat. When it's pulled to a colder surface, it releases some temperature. Over thousands of cycles per second, this back and forth motion steadily pumps heat from one end of the stack to the other. You could think of it like a microscopic accordion. Each oscillation is like squeezing and releasing the air repeatedly, moving energy without the need for mechanical pistons or compressors. The efficiency depends on several factors: the gas used, the geometry of the stack, the frequency and amplitude of the sound, and the thermal properties of the stack material itself. Helium, for example, is commonly used because it's light, conducts heat well, and responds quickly to pressure changes. Another important factor is timing. Basically, making sure the gas moves in sync with the sound waves. If the gas compresses or expands at the wrong moment, the device won't pump heat efficiently. Engineers design the system so the gas is always in the right place. When it's moving toward a hot surface, it picks up heat, and when it's moving toward a cold surface, it releases heat. This is what allows sound waves to steadily move heat from one end of the device to another. If the timing's off, the system can waste energy and fail. In short, thermoacoustic cooling can take advantage of the natural relationship between pressure, temperature, and volume in gases, and then amplify that relationship using sound waves and resonance. By carefully engineering the stack, resonator, and driver, scientists have turned a phenomenon once observed as a curiosity into a powerful practical method of cooling. Now that we've explored the science, let's look at how engineers turn that science into actual devices. Designing a working thermoacoustic cooler is a challenge that requires careful attention to geometry, materials, and energy flow. At first, the device may seem simple. Just a drive, a tube, and a stack, but each component must be optimized for the system to move heat efficiently. Like I said, the basic layout of a refrigerator includes three main parts. The driver acts like the engine, the resonator tube guides the sound, and the stack is where the heat transfer actually happens. Engineers must decide the exact dimension of the resonator tube, the shape and spacing of the stack, and the frequency and strength of the driver. Small changes in any of these can make a big difference in performance, so precision is crucial. One of the main engineering challenges is managing heat flow outside the stack. Even if the stack efficiently moves heat along its length, any heat leaking from the hot side to the cold side, or from the system to the surrounding environment, reduces overall efficiency. To address this, modern designs often include heat exchangers at both ends. The hot side exchanger releases heat into the environment, while the cold side exchanger draws heat away from the object being cooled. These exchangers are carefully designed to minimize resistance to heat flow while maintaining the proper temperature gradient. Material choice is another factor. The stack needs to conduct heat just enough to allow energy to move from the gas parcels without losing too much to the rest of the device. Metals like aluminum and copper are common, but advanced ceramics and 3D printed composites are increasingly being used in research prototypes because they have potential to be even more efficient. This efficiency comes from the material's ability to withstand repeated thermal cycling and offer unique shapes that can optimize the heat transfer process. Engineers often experiment with different resonator geometries. While a straight tube works, it's the most traditional way, more complex shapes, like tapered or looped resonators, can improve the amplitude of standing waves and reduce energy loss. Some systems even use multiple resonators connected together to amplify the effect or to cool multiple points simultaneously. Recent innovations have pushed thermoacoustic cooling into new areas. Miniaturized versions can cool electronic components without fans or liquids, which is especially useful for sensitive lab equipment or compact devices. Larger systems are being tested for household refrigeration and air conditioning, aiming to replace conventional compressors with quieter, more environmentally friendly alternatives. In the realm of cryogenics, specially designed stacks and high-frequency drivers are capable of reaching extremely low temperatures, opening possibilities for physics experiments and medical applications. Finally, engineers could continue to refine the driver itself. While early systems relied on standard loudspeakers, modern designs use specialized high-power drivers, capable of producing precise, high-frequency sound waves with minimal energy loss. One challenge in doing this, however, is that to have a good cooling system, your sound waves have to be very high energy. And often, this means very loud. What engineers are doing to combat this, however, is using sound waves with frequencies so high that engineers can't even hear them. Almost like a dog whistle. Combined with carefully tuned resonators and stacks, improvements like these are gradually making thermoacoustic cooling a viable engineering solution. Looking ahead, the potential is enormous. Researchers and engineers are exploring ways to integrate this technology into everyday life, from appliances to industrial systems. One promising avenue is portable, compact cooling devices. Imagine a small cooler for camping, or a medical transport that runs quietly and efficiently without chemical refrigerants. By relying on sound waves instead of compressors, these devices could be lighter, more durable, and safer for the environment. In addition to small-scale applications, thermoacoustic cooling can transform how we manage climate control in buildings. Engineers are experimenting with larger systems, capable of replacing conventional air conditioners. These systems could use renewable energy sources like solar or wind to drive the sound waves, providing sustainable cooling solutions in hot climates or areas with limited electricity. The quiet operation of thermoacoustic devices also makes them appealing for urban environments where noise pollution is a concern. Scientific research stands to benefit as well. Cryogenic applications, which require extremely low temperatures, are traditionally expensive and complex. Thermoacoustic cooling offers an alternative. Devices capable of reaching very low temperatures without moving parts or dangerous components. This could make advanced experiments in physics, chemistry, and medicine more accessible, especially in smaller labs or mobile setups. There's also a growing interest in hybrid systems. Engineers are exploring combinations of thermoacoustic cooling with traditional refrigeration to increase efficiency, reduce energy consumption, and minimize environmental impact. In the long term, these systems could be scaled up to support industrial processes, cold storage facilities, or even transportation of perishable goods without greenhouse gas emissions. Finally, the adaptability of the technology means it could be applied in ways we haven't yet imagined. Wearable cooling devices, electronic cooling, and compact handheld devices, or even futuristic architectural integration could become practical as engineers refine materials, drivers, and designs. Thermoacoustic cooling has the potential to shift the way we think about temperature control, making sustainable, efficient cooling a more achievable goal for both industry and daily life. Despite its promise, there are challenges. The main issue is efficiency. While the physics is sound, current devices often require significant energy input to achieve substantial cooling. Engineers must carefully balance the driver, resonator design, and stack geometry to maximize performance without excessive energy loss. Another challenge is scalability. Small devices for electronics or lab applications work well, but building larger systems capable of cooling entire rooms or buildings is far more complex and could potentially be one of the best applications. Noise and vibrations can also be concerns, particularly at lower frequencies where the sound becomes audible. While ultrasonic drivers that have too high frequencies for us to hear can mitigate this issue, careful engineering is required to ensure devices remain practical for daily use. Finally, cost is a factor. Advanced ceramics, metals, and precision drivers improve efficiency but can be expensive to produce. Engineers are actively researching to reduce material cost and improve durability so that cooling becomes competitive with conventional refrigeration methods. Thermoacoustic cooling is a fascinating example of how science can take something as ordinary as sound and turn it into a powerful tool. By orchestrating pressure waves and gases, engineers can move heat in ways that seem almost magical. But they're grounded entirely in basic physics principles that even you can understand. From early experiments over a century ago to today's research prototypes and miniaturized devices, the technology has moved from a curiosity to practical potential. It offers a quiet, safe, and environmentally friendly alternative to conventional refrigeration, with applications ranging from household appliances to scientific discovery. Looking to the future, thermoacoustic cooling could reshape how we manage temperature in everyday life, opening doors to portable cooling, energy-efficient buildings, wearable devices, and advanced scientific equipment. At the same time, engineers continue to tackle challenges like efficiency, scalability, and cost, gradually turning what once seemed like a laboratory curiosity into a real solution. In the end, thermoacoustic cooling reminds us that innovation often comes from unexpected connections, like combining sound and temperature. It encourages us to look at familiar phenomena in new ways, to imagine what might be possible, and to apply curiosity to solve real-world problems.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.